In the last video we talked about vector spaces and vector norms. In this video we will talk about a very similar thing, a norm not on vectors but on matrices. This is not a big step because a matrix can be seen as a vector if you want to. But let's see what is a norm on a matrix. And now what will follow? It will follow three properties, the same, more or less the same properties as we have seen here for vector norms. Now we name it M1 instead of V1, this one we name it M2 instead of V2, and this one we name it M3 instead of V3. The norm of a matrix is a number, and this number is never negative. It can be zero, but only if and only if and only if the matrix is the zero matrix. So if the matrix is the zero matrix, the norm must be zero, and if the matrix is not the zero matrix, so there's at least one entry unequal to zero, then the norm is not allowed to be zero. So M2 and M3, and then there are two typical matrix norms. There are much more than these two, but these are the most important ones. That's the row sum norm and the Frobenius norm. And now let's talk about the row sum norm. And let's talk about this row sum norm in examples. That's more easy to understand. So give me a matrix. Your question should be now which size of the matrix. We said that we talk about that only for quadratic matrices. To be honest, the concept of a norm is not restricted to quadratic matrices, but we will restrict on that because we will not need it for not quadratic matrices. So which size? Let's say 3 by 3. Please give me 9 numbers, and now you can give me your numbers. Maybe you give me these numbers. And the row sum norm is the following. Let's add these three numbers, but not add the numbers by themselves, but the absolute values of these numbers. So absolute value is 3, 5, and 2. And now add 3, 5, and 2. This is 10. So we have a 10. But let's check the second row. It's 1 and 7, it's 8. And let's check the last row. So this is 4. Then take the maximum of these numbers, and this is the number 10. So the row sum norm of this matrix is 10. Now let's check if these three properties are indeed true. If we take the absolute values, then the least answer is 0. If we add three numbers, in this case because it's 3 by 3, then if you add three numbers, it must be a number more than 0. And if you take the maximum of numbers which are all more or equal to 0, then this must be a number more than 0, or 0 is also possible. But when is a 0 possible? If the maximum is 0, 0, 0, so only if all entries are 0. So this is indeed true. The norm, this norm is at least 0, and the answer 0 is possible, yes, but it's only possible if and only if the matrix is the matrix consisting only of 0 entries. We can prove all that also. Being a mathematician, you can prove that, but I think it's a waste of time if you are not a mathematician. So allow me that I will not give the proof here on this paper. So let's check if this is true. So which number should I use? Let's say we use -2 times. And what do we get? So let's first multiply, then we get -6, -10, 4. And now let's add these numbers, their absolute values. So 6 plus 10 is 20, 16, and 8. And this is 20. And 20 is the same as absolute value of -2 times. So that is true indeed. So let's check M3. Please give me two matrices of size 3 by 3 and then we can check. Okay, let's take the first matrix to be this one. And now give me a second matrix. And if it's possible for you, please give me a matrix such that the equal is true. So what can you give me? Maybe you give me the correct answering as follows. Let's say 1, 1, 1, 2, -2, 1. These entries are more or less whichever you want to. And now for getting an equal, we need the maximum in the first row. So we need more than 5 in the first row. And we need the same signs as these 3. And so maybe you give me 2, 2, and -2. And now let's check. We get 5, 7, 4. 5, 7, 4 is 16. And the other ones are 2 and 8 and 1. This is 11, less than 16. And 0, -1, 1. So we get a 2. And so indeed 16 is the answer here. And what is the answer if we do it like that? Then we get a 10 off here and we get a 6 compared with 3 compared with 5. So we get a 6 and so we get 16. And so it's indeed true that the norm of that is less or equal to the norm of that plus that. And maybe a second example. And now a second matrix. How can we do? Let's swap these two lines. And this time we have 5 and 3 is 8 and 1 is 9. So we have a 9. Then here we have a 2 and a 8 and a 1, so 11. And here we have a 0, a 3 and a 1, so 4. And so we have 11 here, and let's compare. And here we have a 10 plus a 6 here in this line, so a 16. So the norm of that is less or equal to the norm of that part plus the norm of that part. So in these two examples, it's true, and we can prove, you can prove that it's always true. But I don't want to give this proof. But this proof is not that interesting. The idea of the proof is you get an equal if you have the maximum of the two parts in the same row, and if you have the same sign in all entries of that row. And if you don't have this situation, then you will get a smaller because larger is impossible. So this is the row sum norm, and we will use that row sum norm in the next videos. And then there is more than only this norm. An important one is Frobenius norm, but it's not important for us. And what does that look like? That looks like the Euclidean norm. But as I said, we don't want to go into the details. We don't need the Frobenius norm in the further context. And so there's a lot to say, but we will not talk about that in this video. So that's all what I wanted to say about matrix norms. And in the next video, we will talk about a link between vector norms and matrix norms, consistency. Then we will talk about Banach theorem, and then we can prove the convergence of the Gauss-Seidel algorithm. And for this proof, we will need these things. Maybe you say, okay, I will never need things like that. But if you really want to understand the mathematical reason why it's 100% guaranteed that Gauss-Seidel in the Jacobi iteration converges if the matrix is diagonal dominant, then you have to understand this stuff. Okay, that's all.